Let's talk about the unsung hero of our modern world, the Programmable Logic Controller, or PLC. Seriously, these little boxes are the invisible brains running just about everything, from the factories that build our cars to the traffic lights that get us home. They are everywhere. So let me ask you a question. Think about a super fast bottling plant, a citywide traffic grid, and a giant car factory. What on earth could they possibly have in common? What's the secret sauce that makes them all work? Well, the answer is they all have a brain, an invisible, tireless brain that's making thousands of decisions every single second. It takes in information, it thinks, and it acts with insane precision. And that brain, that's the PLC. So to really get what makes these things tick, we're going to take a tour inside. Here's the plan. First, we'll see why they were even invented. Then we'll check out their core parts, how they sense and control things, how they actually think, and finally, we'll peek into their hidden world of data. Let's do it. All right, first up, why PLCs were invented. You know, to really appreciate the genius of the PLC, you have to understand the nightmare it replaced. A world of tangled, inflexible, hardwired control. I mean, just look at the difference here. Before PLCs, if you wanted to automate something, you had to physically wire everything. And I mean everything. Way Bolton's textbook on this stuff paints a crazy picture. Imagine giant cabinets filled with hundreds of electromechanical relays, all connected by a massive bird's nest of wires. If you needed to change one tiny piece of logic, you'd be in there for days, maybe weeks, physically rewiring the whole mess. The PLC changed the game completely by swapping all those physical wires for a simple program. Okay, so what's the magic that makes this programmability possible? Let's pop the hood and look at the core of the machine, the brains of the whole operation, the CPU and memory. At its heart, a PLC is basically a ruggedized computer, and Bolton's research breaks it down into three key parts. First, you've got the CPU, the central processing unit. This is the actual brain doing all the thinking. Then you have the memory, which is where the program and all the working data are stored. And then, and this is so important, you have the I/O system. Think of this as the PLC's nervous system. It's how the brain connects to the real world. And this brings us to the I/O system. This is where the digital brain of the PLC actually meets the grime and grit of the physical world. This is what gives the PLC its senses to feel and its muscles to act. So let's start with the senses, the inputs. This is how the PLC knows what's going on. It could be an operator pushing a button, a sensor seeing a box on a conveyor, or a switch telling it a safety door is closed. It's all just information coming in. Now check out how an input signal actually gets to the brain. It's so clever. Based on diagrams from Bolton's work, when an operator presses a button, it sends a 24-volt signal to the PLC. But that rough, high-voltage signal doesn't go anywhere near the delicate CPU. Instead, it hits a component called an optoisolator. It basically just lights up a tiny internal LED. That light then shines across a physical gap and hits a light sensor on the other side, which creates a brand new, clean, 5-volt signal for the CPU. That little gap is a lifesaver. It's like a bodyguard, completely isolating the CPU from any dangerous electrical spikes from the factory floor. So what does the brain finally see? Well, inside a real Siemens program, that button press just becomes a simple piece of data. For an on or off signal, it's called a bool, which is short for Boolean. It's just a 1 or a 0, true or false. So a signal named MCP1 ready just tells the PLC, yep, the control panel is ready, or nope, it's not. It all boils down to that simple binary choice. Okay, so the PLC has sensed the world. Now what? Well, it has to act, and this is where the muscles come in, the outputs. These are the signals that turn on giant motors, light up warning lamps, and open massive valves. This is how the PLC makes things happen. And the output process is pretty much the reverse, and it's just as smart. The CPU makes a decision and sends out a safe little 5-volt signal. That signal, again, goes through a protective optoisolator. But this time, instead of just sending information, it activates a heavy-duty switch, like a relay or a transistor. And this is the key. The CPU isn't trying to power a huge motor itself. No way. It's just flipping a much bigger switch that's built to handle all that high voltage and current. And looking at some real-world examples from Siemens, these actions are super specific. An output isn't just a vague turn motor on. It could be something precise like A set RP, which tells a robotic arm to set a new reversal point, or A prot zone, which activates a critical safety shield. Every output is a specific, deliberate action. So that brings us to the big question. We know how the PLC senses and acts, but how does it decide what to do? The secret is in its programming language, which is often this beautifully simple visual language called ladder logic. Now, this might look a little weird, but it's actually genius. This is a single line or a rung of ladder logic. It was designed to look just like the old electrical relay schematics so that electricians and technicians could pick it up almost instantly. You just read it left to right, like a sentence. Let's just translate this one into plain English. The first symbol there, the 2 brackets, just means if input 1 is on. The next one, with the slash through it, means and input 2 is off. And the final one, the parentheses, means then turn on the output. See? It's just a simple if and then statement. And believe it or not, entire massively complex automated factories are built out of thousands of these simple logical rules. Okay, for our last section, let's look at the PLC's hidden world. Because modern PLCs are so much more than just logic solvers. They're powerful data machines, constantly talking to other devices and creating this huge invisible network of information. And to give you an idea of the scale we're talking about, get this. According to Siemens, a modern S7 1500 PLC can send and receive up to 64 kilobytes of data in a single communication cycle. Now, 64K might not sound like a lot these days, but that's roughly the amount of text in a short novel. And it's moving that much information back and forth many times per second. It's just incredible. And to manage all that data, PLCs use the same kind of networking languages as the internet, like TCP and UDP. The way to think about it is this. TCP is like sending a certified letter. It's super reliable, it makes sure the message got there, and it's perfect for critical data. UDP, on the other hand, is like shouting across a room. It's insanely fast, and it's used for things where speed is everything, like controlling a robot arm in real time. So there you have it. The PLC started out as a clever way to replace a cabinet of wires, and it's evolved into this powerful, connected data hub that literally runs our world. It was the very first step in making our machines truly intelligent. And that leaves you with one final thought, right? As these things get even smarter, more connected, and start integrating with things like AI, what will they be capable of tomorrow? What does the future look like when this invisible brain is 1,000 times more powerful?